Hello everyone, welcome to the 14th lecture of the course Statistical Thermodynamics. The topic of this lecture is the most probable distribution for large numbers. In the previous lecture, we have seen that for a simple chemical system in equilibrium, namely 800 hydrogen atoms and 200 deuterium atoms, in a box, there are several possible distributions of H2, B2 and HD molecules. The distribution keeps on changing as molecules break and form. You can imagine that there is some catalyst in the box which allows this to happen quickly. So, the system is constantly changing at the microscopic level, but at the macroscopic level, the system is in equilibrium and is not changing. Moreover, the different distributions have well-defined probabilities. In the present lecture, we will learn something really interesting about distributions. We already know that there are a certain fixed number of ways associated with a distribution, and this is a fraction of the total number of possible ways. Moreover, we know that entropy of a system is equal to the Boltzmann constant times the natural log of the total number of ways. We will see in this lecture that to calculate entropy of a system with a large number of particles, it is enough to know the number of ways in the most probable distribution. We do not really need the total number of ways to calculate the entropy. Let us start with a small system and build up our story from there. Consider the tossing of 4 coins. How many unique outcomes are possible? What are the various distributions possible, and what are the number of ways in those distributions? What is the probability of the most probable distribution? It is very easy to calculate the total number of unique outcomes. So coin 1 has 2 possible outcomes, coin 2 has 2 possible outcomes, coin 3 has 2, and coin 4 has 2. So the total number of outcomes is 2 times 2 times 2 times 2, that is 16 ways, or 16 total outcomes. Let us see what are the different possible distributions. One distribution is when the first one is heads, the second one is heads, third one is heads, and the fourth one is heads. We can label this distribution as 4 heads, 0 tails. Another outcome could be when the first coin is tails and the other coins are heads. Or the second one is tails and the others are heads. Or the third is tails and the other are heads. Or the fourth is a tail and the others are heads. Now all these 4 outcomes can be categorized as the distribution which we can label as 3 heads, 1 tail. And then there are the outcomes where there are two heads and two tails. Let's list out all these possibilities. These ways are part of the distribution which we can label as two heads and two tails. And there will be two more distributions which I will just write down and not list because I'm sure you will be able to do that easily. And those two distributions would be one head, three tails. This would have four outcomes, and there is zero heads and four tails where there is one outcome. There are clearly five different distributions corresponding to the 16 total outcomes in this four coin toss problem. The next thing we are interested to know is what is the probability of these different distributions, and in particular, what is the probability of the most probable distribution. To calculate the number of ways and the probabilities, it can be helpful to map this problem onto a problem of balls in bins. That is, this problem is equivalently that of four distinguishable balls in two distinguishable bins. This is essentially identical to the four coin toss problem. So suppose here are our two boxes, box 1 and box 2, and let's say box 1 has ball 1, ball 3 and ball 4, and box 2 has ball 2, then this is equivalent to the outcome heads, first coin being heads, the second coin in box 2 being tails. We could label box 1 as heads and this is tails. So coin 2 is tails, coin 3 is heads, and coin 4 is heads. The first ball can be put in the boxes in two ways. The second ball can be put in the box in two ways, the third in two ways, and the fourth in two ways. So there's 16 total number of ways, just like in the coin toss problem. Now, the ways of getting three heads, that is, three balls in box 1, is 4 factorial, which is the number of ways in which the four balls can be arranged, divided by 3 factorial. So all these permutations don't count because as long as the ball is in the first box, their order does not matter, divided by 1 factorial for the ball in the second box. So the number of ways of putting 3 balls in box 1, or equivalently, the number of ways of getting 3 heads is 4. In general, the number of ways of getting n heads is equal to n factorial divided by number of heads factorial divided by n minus nh factorial, or this is ncnh, where the notation here is of a binomial coefficient. Using this formula, we can easily get the number of ways of getting 0 heads, that is 4 factorial divided by 4 factorial, 0 factorial, that is 1. The number of ways of getting 1 heads comes out to be 4, and the number of ways of getting 2 heads is 6. The distribution with 2 heads is the most probable distribution, and the probability of this most probable distribution, or the probability of 2 heads, is 6 divided by the total number of outcomes, which is 16, and that is about 37.5%. The reason I write this as a percentage is that I want to compare how the probability of the most probable distribution changes as I increase the number of coins or increase the number of balls in the two boxes. So for 4 coins, the probability of the most probable distribution, which is probability of 2h, is 37.5%. Now let's calculate the probability of the most probable distribution for 6 coins. And the probability of 3 heads will be 6 factorial divided by 3 factorial, that's the total number of ways, divided by 64, 2 to the power of 6, and that comes out to be 31.25%. And if I do this for 8 coins, then the probability of the most probable distribution is 8 factorial divided by 4 factorial, divided by 256, which is 27.34%. And if we go to 8 coins, the probability of the most probable distribution is 10 factorial divided by 5 factorial, divided by 1024, which is 24.6%. We can clearly see that the probability of the most probable distribution decreases with increasing number of coins. Let us now explore the relative probability of the most probable distribution with increasing number of coins. So we want to know what is the relative probability of the most probable distribution with respect to the other distributions as we increase the number of coins. Let me consider 10 coins and list down the number of ways and the relative probabilities of the different distributions. NH is the number of heads, NT is the number of tails. This column will be for number of ways in the distribution, and this column will be the relative probability of the distribution. One distribution is when we have 0 heads and all 10 tails, and the number of ways this can happen is just 1. that is, all the coins have to be tails, and the probability of this distribution can be calculated by dividing this 1 by the total number of ways, and then further, the relative probability can be obtained by dividing this probability by the probability of the most probable distribution. Then the relative probability of this distribution comes out to be 0.004. Another distribution is when there's 1 heads and 9 tails, and there are 10 ways of obtaining this, the relative probability comes out to be 0.04. Then there's the distribution with 2 heads and 8 tails. The number of ways is 45 and the relative probability is 0.18. 3 heads and 7 tails, the number of ways is 120 and the relative probability is 0.48. 4 heads and 6 tails, number of ways 210, relative probability 0.83. And the most probable distribution, where there are 5 heads and 5 tails, the number of ways is 252, and we have calculated the probability of this before, and by definition the relative probability of this is 1, because the relative probability in all these cases are with respect to the probability of the most probable distribution. You can continue doing this for 6 heads and 7 heads and so on, and these numbers can be easily obtained using the symmetry of heads and tails. So clearly the number of ways for 6 heads will also be 210, the same number for 6 tails. The important point is that the relative probability of getting 40% heads is 0.83. Now suppose we had 100 coins and we made a very similar table as we have done above. Without explicitly doing the calculations, let me write down the numbers so that we can look into the kind of insight that we want to get from here. So the number of heads, number of tails, number of ways, and relative probability. The distribution with 40 heads and 60 tails, that is 40% heads, has 1.37 times 10 to the 28 ways in which it can be obtained. And interestingly, the relative probability of this is 0.14. The distribution with 49 heads and 51 tails, that is, the one with 49% chance of getting heads, is 9.89 times 10 to the 28 ways. And the relative probability of this is almost that of the most probable distribution. It is 0.98. And for the most probable distribution, 50 heads and 50 tails, here is the number of ways, and by definition the relative probability of this is 1. The most important take home from the slide is that the relative probability of getting 40% heads is now only 0.14. It was 0.83 with 10 coins and it is 0.14 with 100 coins. Let us see what happens to this number if we go to 1000 coins. For perspective, I'm going to write down the key results for 10 coins and 100 coins before calculating these numbers for 1000 coins. Now we'll write the results for 1000 coins, and before I write the results, for practice, it'll be great if you could do this yourself. So pause the video here and calculate the probability of getting 40% heads with 1000 coins, that is 400 heads and 600 tails, and similarly calculate the probability of getting 49% heads, that is 490 heads and 510 tails with 1000 coins. Also consider what your intuition tells you about what these relative probability numbers should be for 1000 coins relative to 100 coins. Pause now. Let us now calculate these numbers. Let me go to the next page for that and come back to this page to write the result after finishing the calculation. The number of ways for getting 40% heads is 1000 factorial divided by 400 factorial divided by 600 factorial. Now 1000 factorial is a huge number and you will not be able to do this on your regular calculator. As indicated in an earlier lecture, you can use the Stirling approximation to calculate this large factorial. Let me work this out explicitly here. The Stirling approximation is ln of n factorial is approximately equal to n ln n minus n. So ln of 1000 factorial is approximately 1000 ln 1000 minus 1000, which is equal to 6907.76 minus 1000, which is 5907.76. So 1000 factorial is e to the power of 5907.76, and converting to base 10, this becomes 10 to the power of 2565 approximately. Similarly, using the Stirling approximation, we can calculate 400 factorial, which comes out to be 10 to the power of 867, and 600 factorial, which comes out to be 10 to the power of 1406. And so the total number of ways of getting 40% heads, which is this expression 1000 factorial divided by 400 factorial 600 factorial, comes out to be approximately 10 to the power of 292. The number of ways in the most probable distribution, that is of getting 50% heads, comes out to be 10 to the power of 301. And from this, we can calculate the relative probability of getting 40% heads, which we will enter into the table on the previous page. The number of ways of getting 40% heads, or 400 heads when we toss 1000 coins, is 10 to the power of 292, which is a huge number, but the relative probability of this relative to the most probable distribution is really tiny. It is 10 to the minus 9. The number of ways of getting 49% heads is approximately 10 to the power of 301, and the relative probability of this with respect to the most probable distribution is 0.82, which is quite significant. And the number of ways in the most probable distribution, that is 50% heads, is also approximately 10 to the power of 301, although clearly this number is larger than the number with 49% heads. The rounding off is making them look the same. The relative probability here is 1 by definition. Let me quickly show you how to get this 0.82 as the relative probability for 49% heads. So in the next sheet, I will write out this calculation. 49% heads divided by 50% heads will be 1000 factorial divided by 490 factorial 510 factorial, the whole thing divided by 1000 factorial 500 factorial 500 factorial. This is equal to 500 factorial divided by 490 factorial 510 factorial. Now all these factorial numbers are very large, and to calculate them individually and then divide can lead to large errors. So we can note that most of the terms in the product cancel out in the numerator and denominator, and the terms that actually remain are 491 by 501 multiplied by 492 by 502 and so on till 500 divided by 510. There are a total of 10 terms, and each of these terms are close to 1, just a little smaller than 1. And if we multiply them out, this gives 0.82, which we have written in the table on the previous page. Now look very carefully at the numbers on this page and try to understand what these numbers are telling you. We note that the relative probability of the most probable distribution, that is the distribution where 50% of the coins show heads, keeps increasing with respect to the distribution corresponding to 40% heads. In the case of 10 coins, the probability of the most probable distribution is close to the probability of getting 40% heads. The probability of the MPD is much larger than 40% heads when we go to 100 coins, and in the case of 1000 coins, the probability of the most probable distribution is much larger than that of getting 40% heads. In fact, the probability of getting 40% heads is trivially small when we go to 1000 coins. In other words, the relative probability of 40% heads decreases with increasing number of coins. The second important thing to note is that the actual number of ways or outcomes on tossing keeps increasing exponentially as we increase the number of coins from 10 to 100 to 1000. We can calculate an entropy corresponding to each of these systems of a particular number of coins. It may be a little hard for you to associate entropy with the system of coins, so let us map this system onto an equivalent system of particles. You will realize that the system of n coins is exactly identical to the system of n particles or n ideal gas atoms in two connected boxes like this. So this is one box, the left box, and here is this other box, which is the right box, and there is a partition in between the two boxes, which is just a wire mesh or a thin cloth whereby particles can freely move from one box to another. So each particle is like a coin and it can be in one of two states, just like a coin. A particle can be in the left box, which is one of the states, or it can be in the right box, which is the other state. The most probable distribution is when there are exactly 50% particles on the left side and 50% particles on the right side. Another distribution, for example, is when there are 40% particles on the left side and 60% on the right side. This would correspond to 40% of coins showing heads and 60% tails. I hope you are able to see the one-to-one correspondence between the coin toss problem and this one. Now let us calculate the entropy of the system of 1000 gas particles. The entropy is K ln the total number of ways, and the total number of ways here is 2 to the power of 1000. This is the total number of ways in which the particles can be in the left side or the right side, or the total number of outcomes when we toss 1000 coins. This is equal to K times 1000 ln 2, which is equal to 693.15. As an experiment, let us calculate K ln W, where W is not the total number of ways, but the number of ways in the most probable distribution. That is equal to K ln 10 to the power of 301 from our previous discussion, and this is equal to K times 301 ln 10, which is 693.08. The log of the total number of ways is so close to the log of the number of ways in the most probable distribution. Now this is not very intuitive because clearly there are many distributions near the most probable distribution which have a very large number of ways. So the number of ways in the most probable distribution is not equal to the total number of ways. But the log of WMPD is indeed equal to the log of the total number of ways. Now, how is this possible? Pause the video and try to rationalize this. Here is how we can understand this. For 1000 particles, there are several distributions where the number of ways are very close to the most probable distribution. Let us estimate that the number of ways total is about 100 times the number of ways in the most probable distribution. I think you will agree that this is at most that the total number of ways can be. So then the total number of ways is 100 times 10 to the power of 301. Clearly, nobody will say that the number of ways in the most probable distribution is equal to the total number of ways. Now, let's take the log on both sides and then we will see something really cool. So, ln of W total is equal to ln of 100, that is 2 ln of 10 plus 301 ln 10. And now we can see that although W total is 100 times the WMPD, when you take the log, this is approximately 301 ln 10, which is ln of WMPD. So although the total number of ways is many more times the number of ways in the most probable distribution, the log of these two numbers is not very different. There is still some difference though between these two numbers, but let's see what happens when instead of 1000 particles, we go to a more realistic situation, which is when there are close to an Avogadro number of particles. Suppose there are 10 to the 23 particles. These are in the two box system like this. The most probable distribution is when there are 5 times 10 to the 22 particles in the left box and 5 times 10 to the 22 particles in the right box. As you know, the particles are moving and the number of particles are never the same. So there are fluctuations in the number of particles in the left and right box, which lead to various different distributions. Let us consider an extreme case in which there is a huge fluctuation such that the number of particles in the left box have reduced by 10 to the 21. So the total number of particles in the left box is 5 times 10 to the 22 minus 10 to the 21, and these particles have gone over to the right box. My question to you is that what is the relative probability of this distribution with respect to the most probable distribution? As you would rightly guess, the relative probability of this is very, very small, but I would like you to go ahead and actually calculate this number to make sure that you know how to do it. So pause the video and calculate this relative probability. The answer is that the relative probability is about 1 divided by 10 to the power of 10 to the power of 19. So clearly, this is a ridiculously small probability for this distribution to be realized. But now we come to the really fun part. Even if we say that there are 10 to the 21 distributions besides the most probable distribution which are important. And further, we make this really generous assumption that the number of ways in these 10 to the 21 distributions equal the number of ways in the MPD. Then the total number of ways is equal to 10 to the 21 times the number of ways in the most probable distribution. Clearly, this is a huge overestimate of the total number of ways. The actual total number of ways is probably closer to the number of ways in the most probable distribution than what we have considered here. But even with this, if we take the log of both sides, then we see that ln W total is equal to 21 ln of 10 plus ln of 10 to the power of 3 times 10 to the power of 22, which is a number you should have calculated while answering this question about the relative probability of this distribution with respect to the most probable distribution. And you can see that this is 21 ln 10 plus 3 times 10 to the 22 ln 10. Clearly, this term 21 ln 10 is negligible. And this term is simply the ln of the most probable distribution. So we see in this case with a large number of particles that the ln of the total number of ways is almost exactly the ln of the number of ways in the most probable distribution. This here in the box is the main result that I wanted to get across in this lecture. In conclusion, for a large number of particles, the log of the total number of ways is equal to the log of the number of ways in the most probable distribution. So, to calculate the entropy, it is good enough to just count the number of ways in the most probable distribution. In the next lecture, we will see why this idea is so helpful. See you for the next lecture.